We're building a robot with the goal of automatically recognizing and picking up cigarette butt litter. This is what it currently looks like. Notice a problem? It's a tangle of wires with no clear way to attach new components or expand, and we need a way to work on the robot more easily without having to create a new case every time we need to make an update. And also need to keep the components contained. Our solution? A modular robot.
This is a sketch of our overall vision for the case. The idea is to have trays which slide in and out on these rails here, which will hold electronic components, wiring, whatever is needed. As we come up with new layouts, we will only need to create new trays instead of redoing the whole robot. The sliding trays will also make it easier to work on components in an open area. Essentially, each tray will be a module that can be replaced or updated as need be. We will also have a way to slide the arm and claw unit in and out of the robot, so that if we want to have a new arm design, we don't need to redesign the whole robot, just the arm.
This whole thing should be able to screw on the tracks we already have so that we don't need to reprint those either. And we'll have a door that slides into place so that we can easily access the inside. We started on paper before modeling anything on a computer. First, the base. It needs to be big enough to hold the battery, which is the largest component, with some room to spare for cables. This will determine the width and length of the rest of the case elements. We also made sure to account for adding a track for the door on the back of the bot. The tracks will screw into the base here, here, and here, and we'll need a gap in the walls to allow the wires from the tracks inside the case.
These will be rails that the trays will slide onto. We spaced the bottom tray far enough away from the base to fit the battery, and the other two trays need 3 centimeters of space to allow for all of the electronics to fit comfortably. Our current design will need 2 trays, and we'd like to keep the robot from getting too tall, so this looks about right. After messing around with arm placement some, we determined it would need to be on the front of the robot. We originally wanted it to be on top, but then it would struggle to reach the ground without making the arm a lot bigger. So we updated the design. We also added a hole for the servomotor cables for the arm to get inside the case, and for a camera to be attached in the future.
Now that we had everything laid out with the correct measurements, it's time to put it all into CAD. This all took a lot longer in real life, and we had to learn how to use FreeCAD, a challenge of its own, but we're happy with how all this turned out. It's dope to see everything we laid out on paper taking shape as a 3D model. It feels a lot more tangible, and I'm getting excited to print it on our new 3D printer. Okay, time to print. We just uploaded the file and click slice, and that's a long time. So we'll just show you the sped up version. It took a full day just to print the main case, and we have a pretty fast printer. I'd been wanting one for ages, but with our robotics need becoming more complex and the process of printing at the library becoming more arduous, it was finally the right time to pull the trigger, so we got one as a combination birthday/Thanksgiving/Christmas present.
After everything is out of the printer, we need to remove the supports and get to assembly. Where did that go? There we go.
Oh, this is fun. See, this is the fun part.
The assembly?
The recording. And then since you have a really good camera, kind of...
It does the hard work for you?
Yeah. And you can kind of like zoom in.
After the supports are removed, we need to attach the tracks to the housing. I'm really hoping they fit because reprinting all of that again will take a long time. And perfect fit, nice. We found the STLs for these tracks on Thingiverse, and they do a great job for now, but we have some ideas for potential improvements, and after testing outdoors, we may make some tweaks to their design. Because they just screw in here, as long as we make the mounting points the same, we can easily design and print new tracks if we want to.
We also need to design the trays in CAD so that we can print those too. The trays include standoffs for the electronics so that they have sufficient airflow and gap for cable routing. This only takes about 4 hours to print and it fits perfectly. The top tray will hold the breadboard and wiring and the lower tray will hold the Raspberry Pi. We're now using for the computing and controls. Just one small problem. With the Raspberry Pi screwed on there isn't enough room to attach and route the power cable, so it's time for a new design.
And 4 hours later, we have just enough room for the cable. This shows exactly how useful the design is. We were able to make updates to just a single tray without having to redo the entire design. Success! Once the trays are printed, we put all the electronic components together and simply slide them into place. It's looking so good. At least that's my opinion.
This is a Lego prototype of the claw design. It's way too big for our robot, but it gave us an idea of the mechanisms we'll need to use. This thing, for example, is called a worm gear. So we'll need to design a worm gear in CAD that is the correct size and meshes correctly with the other gears to control the claw. This whole thing attaches to a servo motor to control it. And it slides perfectly into the arm we designed earlier. This is actually designed out of paper. You can watch a previous video to see how we did that. We also 3D printed this attachment so that we can slide the arm in and out of the robot housing to easily replace it. And finally, our arm assembly is complete.
If you've seen any of our previous videos, you know that we recently made the decision to switch from using an Arduino to using a Raspberry Pi. The first step to getting the Pi working was to flash the OS onto a micro SD card. Then I get to write some code for the WebSockets and motor controls, this time in Python. I've written this program in a lot of different versions at this point, and test it. As you might be able to tell, the motor control capabilities of the Raspberry Pi are somewhat lacking. I was just a little bit frustrated since this is something like the third time that we've switched out components. We started with an Arduino Uno, then we updated to a bigger, badder Arduino Giga, and finally made the decision to power it with a Raspberry Pi. Another option would be to use an Arduino for the motor controls and a Raspberry Pi for the brain, but I really want to minimize the complexity of the architecture and not buy more things than I absolutely need. I was lucky enough to have the opportunity to chat with some professional robot builders at a local meetup, and they recommended using both a Pi and an Arduino. I played around with the idea of using our Uno since it's the smallest and cheapest of our Arduino boards, but with room required to run power cables, it wouldn't really fit in our newly minted case. I really didn't want to print a bigger form factor case and was at my wit's end for a few hours until I realized the solution was so much easier than I originally thought. We bought an Arduino Nano for its smaller footprint and connected it to the Raspberry Pi via USB. The Raspberry Pi controls the WebSocket communication and, in the future, will also be responsible for handling the machine learning. The Arduino's sole responsibility is for controlling the motors without making our robot look like it is having a seizure. Time to see if it all works. I'm really hoping it does, because if we have to rebuild it again next month instead of tackling the next problem, it will be pretty demotivating.
Is it recording?
I'm recording now.
Yeah?
Yeah, move forward. Ooh, nice.
Okay, I'm gonna stop it now.
No, return, reverse, or, yeah, and then try to do a full circle.
And now, at long last, we have an actual functioning robot. All it needs now is a bit of AI and of course a name. If you have any ideas for a name or any other ideas, drop them in the comments. And if you want to support this project, we'd love it if you consider possibly clicking the like button, subscribing, or checking out our Patreon link in the description. It would be super nice of you. See you next time.